Okay, I think we can get started. Yeah. So before we start, any questions regarding the assignment project? Anything? Any questions? Yes.
Is there any deadline for the group formation or the initial proposal?
Yes. So the initial proposal probably will release that. The deadline I probably will release soon. So it's better you figure out if you want to do this individually or you want to find a team member. So, but I'll still give you some time to figure that out. Yeah. Okay.
So at least like a week from now is fine.
Yeah, should be a couple of weeks. So, because we are not in the urgent to. I mean, because we just started, right? So you always have to. I don't know, like if everybody come to the class every day, so you may have to meet someone. I'm not sure, like how do you guys gonna find a partner? So that's another issue. Like if you want to do group project, I think the web course, they have some discussion panel. Maybe or if you can put a sign-up sheet, like I'm looking for a team member, right? So you can put some notes, right? I only have very basic, but you have already an idea. Let's say you want to do some like X-ray or MRI or breast cancer diagnosis, right? So this is your project idea. Then you say, okay, I'm looking for a partner, right? See if any other student want to join you, right? So if you don't want to actively looking for somebody, so this may be another way to figure out a partner for yourself. Yeah. Okay. Okay. Yeah, but I think for the project, if you don't have any idea, like this is the first time you are getting into medical imaging, I think a Kaggle probably the best choice for you because the problem, the data set, the evaluation metric, or they may provide some baseline method is already there. So it's really easy for you to get started, right? So also looking to some of the MICAI conference, right, the workshop or competitions. So they are well-defined problems. And there's a lot of resources you can use. Okay. All right. So today we'll continue talk about some of the basics of deep learning, right? So last lecture we kind of quickly go through the basic building blocks of the neural network, specifically convolutional neural network, because we're dealing with image processing, computer vision, right? So we talk about convolution, pooling, and also the optimization, right? So we have the basic, stochastic gradient descent, and how we can specify the learning rate, how we can do the optimization. And just to give you an example, right? So here, if we want to, let's say the PyTorch is your chosen deep learning framework, which a lot of people are using PyTorch now. So you can, in the PyTorch, then you can easily specify what kind of optimizer you want to use, right? So here I have two options, right? So one is the SGD, which is the very basic, commonly used optimizer for optimization. So then you can call this function, and here you can specify a couple of parameters, right? So the most important is the learning rate, okay? So here I also have a momentum parameter here. So that's actually using SGD plus the momentum, right? So the momentum is basically trying to accelerate the convergence, right? Because we want to build upon the previous optimization step, right? So we want to see, okay, which direction this optimization go to, then we can take that, to accelerate the convergence. So you can also specify the parameter for the momentum, basically specify the velocity from the last step, okay? And this is the, just a basic equation, right? So how the SGD with momentum is working, right? So you have this, learning rate with the gradient from the last step t, right? So this is your current step, t plus 1. And here, so the vanilla SGD don't have the extra term here, right? Don't have the momentum, but now you have a momentum here is able to help to accelerate the convergence. Then you can also using the Atom optimizer, right? So Atom optimizer is more like advanced optimizer. So basically combine these adaptive learning rates and the momentum, right? So we also discussed, right, the learning rate has a big impact on your final performance and also how your model is trained, right? So we have some specific guidelines, right? Maybe you want to have specific, learning rate scheduling, right? So Atom is automatically taking care of these. We have this adaptive learning rates and plus the momentum, okay? So beside these, right, so we also have other, optimizers, right? These IMS prop, right? So Atom W here. So the question is, so what kind of optimizer, right? So since we have these many options, which one should I use, right? So if I just get into this field, I don't know much of the experience, which one do I use, right? So I think if you just get into this field, right, the very basic you can use is maybe SGD with momentum, right? So this is easy to tune, right? You only have 2 parameters. And also you can using Atom, right? So because it has the adaptive learning rate, so you don't have to very carefully babysitting the learning rate so to train your model. Okay, so those probably the go-to optimizer, or you can consider those are the default optimizers you want to use. Okay, so next I also want to talk about the interpretability of the deep neural network, right? So it's basically how we can explain the decision that is produced or generated by the deep neural network, right? Because this is really important for many real-world applications, right? So for example, the autonomous driving, right? So I want to know why do you make a brake? Why do you accelerate? Why do you want to change the lane, right? So how the model is making such a decision based on what kind of observation, right? And of course, for our class, right, medical image computing, medical diagnosis, we definitely want this kind of explainability, right? So if the model detect there's a tumor or, detect somewhat of a normality of the medical images, so what kind of insight or what kind of information the model is based on, right? So we want to have some explanation, right? So, and also the physician, right, or the doctor may be based on that and see if the model is actually making something useful or we have to make some correction. So there's a lot of policies and regulation requires that, right? So actually this has been rigorously enforced, right? So because eventually AI is going to be used everywhere in our daily life, right? Because we already see the tremendous potential of AI, right? So there's going to be a lot of policies and regulations, right, to enforce this kind of interoperability. So there are some simple sort of like explanation, right? So what kind of, why the neural network is making such decision, right? So the very fundamental or very simple form is we can actually visualize, right? So in the last lecture, so we've kind of overviewed a little bit, right? So this is a very simple, CNN network like the Alex ResNet, right? So different neural CNN network architecture. And we can actually visualize these kernels or filters from different layers. So that give a sense, right? So what is exactly are these filter, pick up what kind of information, right? So what kind of information these, parameters actually, extract from these data, input data.
Professor,
yes.
Can you go into the previous slide? How does it mean the ResNet 18? The 18 terms, the 101 terms, what does it mean?
Which one?
I mean the ResNet -18, they have said, right? Model name.
Yes.
18 refers to what? It's the layer of model?
Yeah, so that's the layer. So how many layers? So the ResNet have different depths, right? So we mentioned you can keep stacking multiple CN layers or, pooling layers, right? So the ResNet 18 means you have 18 layers of architecture. So the ResNet 101 means you have a much deeper one, 101. And here, a DenseNet is is a much denser. It's another type which is really close to ResNet, but with much more dense residual connection. But it also has 121 layers, so that specify the layers. Okay. So of course we can visualize different layers, right? So all these filters, but that doesn't give much of like how still kind of does not relate it to the decision, right? This only give us a sense, okay, the network maybe learn some meaningful representation, right? So we can detect edges, corners, or complex combinations to detect those information, but that doesn't really tell us, right, why exactly it predict this is an image of a cat or this is image of a dog, right? So another way is we can, further look into the deeper layer, right? So maybe look at the last layer, right? Because that's the close to the softmax make the prediction, right? So this is the fully connect layer. So basically, that's your eventual or the final feature representation, right? So a lot of time, right? So let's say you only using CNN as a feature extractor. You also want to combine with some classic machine learning like random forest, support vector machine. You can actually using a pre-trained CNN backbone than only using the fully connected layer, the feature, right? Then you can using that to also train like SVM classifier, right? So by visualizing or maybe examining the last layer features will also give us some information, right? So how good is that feature representation? So in this example, right, so you can using the last layer feature representation to kind of query or retrieve, right? So for example, I have a test image that I go through this, the very basic AlexNet, right? So I have this last layer, which is 4096 dimensional feature vector. Then I can go through, if I have a database, right, or the test set, I have all these different images. I can also, extract these, go through the CN, run through the CN network, and get the last layer feature embedding. Then I can retrieve, right? So for my test image, what are the closed, the neighbors, right, in the feature space, right? So for this example, right, so the first image, so the test image is a flower. Then I run this feature, and I also run these feature extractor on all the images. I can retrieve the top 6 images, right? So that kind of give us a sense, okay, this feature actually learns something that is related to the flower, right? So that's why in the test set, they are able to retrieve the closed one that's also related to flower, right? So here you have another image, which is an elephant, right? So the retrieved image are also related to elephant, okay? Okay, all right, so that's, you can use the last layer feature to retrieve the nearest neighbor and see how good is the feature representation, okay? And sometimes you may have some failure cases, right? So, this is like a pumpkin with different shapes. Although I think in this case, the features are pretty good, right? So retrieve these pumpkins with different, like Halloween designs, but sometimes this may be confused or have similar appearance, right? So maybe like a clock or something else with the circular shape, right? So that can also give some diagnosis, right? So if you have a really close resemblance of image, so that's why maybe this feature representation will make a false retrieval, okay? And you can also, do some dimensionality reduction, so you can do some visualization, right? So previously, because this is really high dimension, right, 4096, you just have to retrieve the actual image and to do some examination. But actually, you can using some dimensionality reduction algorithm like PCA, right, principal component analysis, to reduce the dimension from 4096 to maybe 2 or 3, right? So which you can plot. So in this case, right, so if we're doing some digit classification, then we can plot these all these different digit examples, the features, and project them into like 2 or 3 dimensional spaces. Then we can visualize these features, right? So this gives you some sense, okay, some of the classes, right? So let's say this is maybe class digit 1, right? So this is maybe class digit 2. So you can see that, okay, a lot of these examples actually being clustered or grouped together. So this is what we want, right? So all these samples belong to the same classes. They are very close to each other, form a very compact cluster. But you may see some samples, right? Maybe that the digit is written in a way, okay, maybe written like this, right? So this could be 1 or 7, right? So some people may be writing different ways. So you might see a digit, supposedly the ground truth is letter 1, but it's far away from the class center, right? So because in written away that is, maybe like a 7. Yes, question?
Is there any intuition on when we might do PCA versus TSNE?
Yes, I'm gonna get to that point. Yeah, so right now, just PCA, I'm just saying you can use in different type of dimensionality reduction because high dimension, we cannot visualize, right? So we have to reduce into 2 or 3 dimension. So the next is we want to do TSNE, right? So TSNE, which is another dimension reduction. So the PCA is a linear dimensionality reduction because you're just finding some of the principal component, right? So which mostly preserve the variance of the total data, right? So then you project the data into those principal axes, right? So do the linear projection. But usually the data is really nonlinear relationship, right? Very complex. So linear dimension reduction or representation may not be the best choice, right? So you can do kernel PCA, right? The kernelized method, which is also nonlinear dimensionality, but another way is, or commonly used, is the TSNE, dimension reduction, which is a nonlinear method. So it will compare this kind of pairwise similarity in the original space using the Gaussian kernels, right? So you're using the kernel method. And also they're using the student T distribution to preserve the local neighbors, and also trying using the KR divergence to minimize the KR divergence between high and low dimensional similarity distribution. So in this case, the local relationship in the high dimensional space will be preserved in this low dimensional space. Okay, so TSNE is mostly preferred over PCA because of the preserve the local similarity, right? Because it's also able to capture these nonlinear relationship in the data, and eventually, if you want to run the TSNE, right? So again, let's using this MNIST digit classification as an example, right? So what you do is you pass your data set through the trained network, right? You can collect the final layer embedding. For example, here, let's just make it simpler, right? 64-dimensional vector for each image. Then you can apply the TSNE reduction to reduce into a 2D representation, right? Then you can plot these data points in the 2D space and maybe color code them according to their specific class, right? So you may end up with a representation like this, okay? So actually you can visualize, you can assign the ground truth with these samples, right? Then you can identify, okay, which of the data points actually may be misclassified at all, which can be an outlier, right? So you can actually go to look at the specific data points, right? Like I mentioned, right? The letter may be written in a way which is close to another different class, okay? All right, so these are some of the visualization, right? So you can, reduce the dimension of the features, and so you can help to visualize. So TSNE is very popular. Let's say if you develop a new type of neural network architecture, or you build a specific module, right? So that, eventually improve the performance, right? Then you want to explain, right? So why your method is able to outperform like ResNet or DenseNet, right? So what kind of benefit is your development neural network? Then you can using the TSNE to visualize the feature. Hopefully, right? So if you compare like the vanilla or the baseline method, right? So these feature may not be clustered where, right? But your method maybe make the intra-class more compact, and the interclass more separable, right? So that's, in that case, the decision boundary can be easily drawn, right? So you have an easy time to have a hyperplane to separate all these different classes, right? Because we have very large margin in between these different classes. Okay, next I'm also going to discuss a more advanced technique, right? So we can also give us more detailed explanation, right? So what kind of information the network is based to give us such prediction, right? So here we have an example image, then we go to some of the CNN, then we make a prediction. This is a cafeteria image with a confidence of the probability of 90% chance that's the cafeteria, right? So this method is called class activation map, right? So basically it's like a heat map, tells you, okay, which region contribute the most to the prediction. This is a conference center, right? So for this example, you can see that, right, this red region, which means has a higher value, so which means these pixels contribute the most to the prediction. This is a conference center. And visually you can see that kind of makes sense, right? So you have a podium, then you have this microphone, right? There's a speaker standing here to give a talk, and then there's audience as questions, right? Also highlight this speaker region. So that kind of give you some intuition, right? So the network is based on these key information or pixel regions to predict this is a conference center, okay? So another image, right? So it shows this is indoor booth, right? So because the highlighted region is in the poster area, right? So, because a lot of indoor booth, right, they have a lot of poster presentations. So that tells you, okay, the network make prediction based on these specific or the highlighted region. So how does this class activation map is generated, right? So this is what they come up with, right? So we have a CNN network, and then let's say this is the last convolutional layer, right? So you have all these different feature map. Then what they do is they're using a global average pooling, right? So global average pooling means for each of the feature map, you just collapse every pixel, the value in this feature map to a single value, right? So basically you take the average of these feature map, you get a scalar, okay? So these are the scalar from different channels of this feature map. Then you go to these, the last layer, like the fully connected, you go to the softmax, right, to generate the class probability, okay? And because of these, right, the class probability is proportional to basically the global average pooling and also multiply with these different weights, right? So these, because of these two sum inside, they are linear relationship. So you can basically put this sum into the same format. So in this case, you will generate basically like a weighted sum of these feature map, right? So this FKHW, which is these feature map, right? Individual feature map. And this W here is basically like the weights for these, the last layer, right? So this is like a weighted sum of these feature map, right? So here is just basically a visual rollout, right? So you W1 multiply this weight, multiply with the first feature map, and W2 multiply with the second feature map, right? And eventually you end up with a single feature map or heat map look like this, right? So for example, this is maybe corresponding to the prediction of class of a dog, right? But I also want to examine, okay, if I want to see, because there's, let's say you have an image net, right? Maybe there's 1,000 of classes. I also see one probability, it predict a cat of, 20% or 10%, right? I also want to see what information the network rely on also give a prediction of a cat, right? Then I can retrieve another different set of weights, right? So I can look at the cat here. What are the weights are connected with the last prediction of a cat, right? So maybe another set of weights, we can call it W1 prime, W2 prime. Then we can also multiply these feature maps, get another class activation map, right? So So the heat map will be totally different, right? Maybe the heat map is no longer highlighting this dark area, maybe some other area. If there happens to be a cat in the scene, right? Maybe only a small portion, right? So that also gonna be possible. Okay, so that's their very basic idea of how to generate this class activation map, right? Like the heat map. So this is an example, right? So here is the image, and we pick the top 3 predictions, right? We can create the corresponding heat map, for these top 3 predictions, right? So predict dome of 45%, right? So this is the heat map corresponding to this dome prediction, right? If you put it as a palace, right, there's 22%, 21%, right? So this is the region highlighting the pixels that give the prediction of the palace, right? The church as well, okay? So that gives you a more detailed diagnosis, right? So like where this, region is actually being highlighted to make this prediction of a specific class. So here, just give you a more example, right? So like this is a lot of, just like a video, right? So we run through the CNN for each of the video frame, and we generate the prediction of a class that belongs to the ImageNet class categories, and we also highlighting. I also show the class activation map, right? So for different classes, which region was mostly highlighted, right? So yeah, if you look at this, right, a lot of time they predict this is prison, which is really interesting, right? So this is like I think this is maybe like a cartridge or something. But you have these kind of bar shape, right? So that looks like, and also like the vertical lines, right, in the alley also feels like, like the prison bars or something like that. So make the prediction. So that gives you some intuition, right? So why this make a, but it also gives you some sense, right? Maybe your data set is biased, right? So you have a lot of maybe samples from the, prison, then that, the model is trained on such images, then they give you this kind of prediction. So that means you have to maybe make your data set more diverse, right? Yeah, the bullet train is also can be, I don't know if you guys see the bullet train, like, the China, they have those high-speed bullet train, the Japan, Germany, right? So their shape is kind of very like a bullet, right? So the speedboat, right, so is also like the front is like a bullet, right? So based on that small information to make a prediction, right? So yeah, I think this is really interesting, give you a more detailed sense, right, how the network is make a prediction on that. Okay.
Seems to be trained on a lot of like prison stuff and military.
Yeah, I mean, yeah. So that might be a possibility. So these, so that also give you a sense. Maybe you have to maybe expand the image, or maybe do some more in-depth diagnosis, right? So you don't want your model to be biased on such of the images, right? So then give this kind of false prediction. Okay. So this also shows some of the failure cases. And so the failure case you already see in the previous example of the video, right? So here just, isolate a couple of, failure cases, right? So this predict a high probability. This is the sushi bar. And you can see why make such prediction, right? So because this is like a bar area, a lot of sushi bars, right? The chef will just standing there and make sushis and go back and forth, right? So, but happens this is like in the indoor household setting, right? And also this prediction, like this is a martial art gym, right? So, and you can see that this is based on the barefoot, right? So the martial gym, I think a lot of your time you have to barefoot, right, to do the training. So that maybe this could be a bias, maybe the model is not trained well, right? So have some bias there. So that gives us some information there. Okay, so beyond just visualization, right? So we can definitely tell, what the network is trying to highlight, make a prediction, but based on this kind of sort of a localization capability, right? So what other applications the CAM, right, class activation map can be used I want you to think about that, right? So besides just simple visualization, what you can use CAM for maybe other tasks? You guys think about that?
Maybe you can show biasness of the data set you have trained on. So
Yes.
you can give more type of generalized type of data.
Yes. So yeah, definitely we can see if there's any bias, but make some diagnosis. But again, that's from the visualization point of view, right? So, but what else? Maybe I want to apply to other applications. Do you think that's also possible, based on that? Okay. But I don't know if you guys notice, right? So they generate this heat map, right? So they highlight this region. Then based on this heat map, we can actually create a bounding box, right? So let's say I'm doing an image classification task. The label we are given is the class label for this image. This is starfish, this is a cat, this is dog, right? This is bicycle. But with this class activation map, we can actually localize, right? So this is the heat map. Then we can put a certain threshold, right? Then we can call per region. Then we can actually localize where that starfish is in the specific example. Then this is object detection, right? Object detection is we want to place a bounding box on a specific object, right? So then we can actually do weakly supervised localization, right? So the weakly supervised, it means we are only given the image level label, right? If this is a fully supervised localization, then the label we should be given for the training should be bounding box. As we know that bounding box is much harder to obtain, right? We have annotators to draw a bounding box, right? You have to spend maybe a couple of seconds each image to draw this bounding box. But for the starfish, right, we can just generate this very quickly, right? So maybe less than 1 or 2 seconds. We don't have to draw any bounding box. So we can using this as a weakly supervised localization task, using image label to actually localize a specific object, right? So actually the authors from this paper actually did this experiment, right? So here, if we using the, let's look at this AlexNet, right? So this is the baseline network. If we're using full supervision, which means we're using the bounding box to do the fully supervised training, we get a localization accuracy of 95.8% of accuracy, right? But for their method, right, so they are using the weakly supervised signal, which is the image label. Don't have any bounding boxes during the training, but using the class activation map, they are also able to achieve 60.9% of localization accuracy, which is very close to the fully supervised, right? So this is really neat, right? So in this case, we don't have to label these bounding boxes, but we have the capability to do the localization. Okay. So that's a very cool applications they using the class activation map. But there's also some limitations for this framework, right? So if you recall, right, so in their framework, they have to using the global average pooling to make each of the feature map into a scalar. Then you can, map out to the weights, right? So to generate these class estimation map. But the global average pooling is not always being used in the architectures, right? Some of the architectures doesn't use in global average pooling. Then in this case, you would have to, if you want to use in CAM to visualize, you would have to maybe change your architecture, right? Maybe adding a global average pooling layer, you have to retrain the network. Then later you can use in CAM for the visualization. To solve this issue, right, we don't want to retrain the network, right? We don't want, because that's going to be very tedious, adding a GAP layer to retrain. So this gradient CAM, right, called gradient weighted class activation map, solve this issue, right? So without changing the architecture, so the way they do is they are using gradient, as a way to weight these feature maps so that you can generate the similar kind of heat map to do the visualization, okay? So I'm not going to dive into the details of the gradient CAM. So if you are interested, you can look at their original paper. But, so this is an improved version of our CAM. Basically, you don't need to you don't require any architecture change or retraining. So you just any architecture you can use. Then basically you can plug in grading CAM to do the visualization. Okay, so this is an example of grading CAM to do the visualization, right? So this is a cat. So actually, this is a very good example because we have two objects in this image, right? A cat and dog. So if we want to see, right, what this network is focused on by making prediction of this cat, and you can see that the network is kind of highlighting the cat region, right? So then we go to the dog class, right? So you can see that the attention or the heat map has been changed, right? So it changed to focus on the face region of the dog, okay? And they also did this weekly supervised localization, right, and compare with the CAM, and they were able to have, comparable or better performance. And so this is a really good benefit for their method because they don't have to change the architecture or retrain the network.
Does GradCam provide the intuition of using the attention in the transformer like that?
Yes. So the grading CAM, so you can also, combine with other, not just CM. Later, people revise it. You can cope with the vision transformer architecture to also do the visualization. But, beside this, people also visualize the attention map in the vision transformer to provide other insight. Yeah. Okay, so talking about the bias in the data set or the model bias, right? So the author in the grading CAM paper actually did this kind of experiment, right? So they show this kind of example, right? So you have input image, right? So if the model is biased, right? So if we look at the first row, right? So a biased model was looking at the face of the person to decide if the person was a nurse, whether the person is a nurse, right? So here, the ground truth is nurse, right? If you look at the activation map or the heat map, right, highlighting the face, some of the hair region, right, and another image which is a doctor, which is not the nurse class, right, and all, it will highlighting the face or the hair region, right. So I think for us, we examine or distinguish, the nurse or a doctor maybe based on some other, well, not based on the gender, right? Because we can have male or female nurse, we can have male or female doctor, right? So usually, for these particular examples, we can look at the color of their, coat, right? So maybe nurse sometimes they have their own color designated, coat, right? Maybe blue, sometimes green, or some pink, right? They have different meanings for their coat. But usually doctors, I know some of the surgeons, they also wear this kind of blue, but most cases, if they are not doing any surgeries, they maybe wear this like a white coat, right? So this is the way they help trying to diagnose this, right? So if the network actually pay attention to the features that is not biased, right? So for this one, right, they call this an unbiased model, and they were able to predict this is nurse not based on the face or hair, but based on maybe the shirt, right? So the shirt region, and for the doctor, they also highlighting the coat and also stethoscope, right? So this is maybe very unique to a doctor. Okay. In the medical image domain, right, so people also using the grading CAM for the glaucoma diagnosis and the localization, right? So if the glaucoma is like a nerve damage, disease, right? So you can using grading CAM to actually localize, right? If you don't have the label for a specific, like a bounding box or segmentation mask of the region, but if you only have the image level label, you can actually using grading CAM to do the localization, right? Okay, so there's a lot of variants, trying to improve upon, right? So there's grading CAM++, I think actually I found a recent, just released a couple of days ago, this finer cam. So they are able to work with multimodal data, right? So have vision and language. Right now we have VLM. So they are also able to work with vision language model. They are able to like tell, different, also detect like difference, right? What's the difference from Grandala, right? So maybe a different type of bird, right? So the network is able to highlight what are the difference. And so if you're interested, you can, look into this paper as well, okay? So here are some of the reference, right? The CAM, grading CAM plus, and this finer CAM, okay? So these are the tools, and all these, diagnosis tools, their code are available, so you're welcome to use them. I think in the first programming assignment, I also mentioned, right? So if you want to using the grading CAM or CAM to visualize, you can try that out, okay? Okay, so this is the implementation. Okay, all right, so before I move to the recurrent neural network, any questions with the part? So I think we are done with the CN, all these. So we'll talk about the recurrent neural network, okay? So here is, the vanilla neural network, right? So far, like we've encountered is like image classification, using CN or maybe fully connect neural network, right? So we have a single input, then we generate a single output, right? We are doing this one-to-one mapping, right? So basically, we are learn a function, right, which is the, basically the parameters of a neural network to map an input, an image to a specific class, right? This is a cat. But for other applications, right, so we may not necessarily, have one-to-one mapping, right? So we may, process, sequences and have like one-to-many mapping, right? So we have one input, but we want to generate like a sequence of output. So, can you think about specific applications that fall into this category, like one-to-many mapping?
Encapsulation.
Which one?
Translation.
Translation. You mean like language translation? That should be many-to-many, right? Because, if could be unless you input a word, you output two words for a different language, right? But usually translation is like many-to-many, right? English to French, Germany, right? So that's many-to-many. The captioning you mentioned, that's specific example, right? So you have an input image, right? And then the output will be a sentence, right? So a sequence of words, right? So you have a one-to-many output mapping, okay? Image, image segmentation is that you have an input image, right? Then you also have an output. In a way, you can consider that could be an output has many different classes, but again, it's still like you have a pixel to pixel correspondence, right? So like you have one pixel has one specific label. Or you can say I have an input image, my output is a single segmentation mask, right? A mask will capture different classes. So it depends on how you interpret, but the obvious example is the captioning, right? So you have a single image, but you output a sequence. You can have like a paragraph, many paragraphs of words trying to describe, right? What happens, what's going on with this image, right? You also have many-to-one, right? So one example is the sentiment analysis, right? You want to classify the sentiment of a sentence, right? So you have a sentence, maybe you are doing some, Yelp review, right? You go to a restaurant, or maybe you IMDb, I think, like for the movie review, right? So you watch a movie, you write a review, right? So in this case, we want to, we have an input, like a sequence of words, sentences, then we want to output, right? If this is a negative, this is a positive, right, or this is a neutral. So sentiment analysis is many-to-one mapping. And we can also, another example is we can consider video action recognition is many-to-one, right? Because we can consider video as a sequence of frames, and we want to eventually make a single action label, right? So what action is happening in that specific video? And of course, we discussed right, many-to-many, right? So this can be machine translation, right? So here I have the English to Chinese, and you can go back for. And video classification can also be considered as a many-to-many case, depending how you are doing this classification task, right? So you can do this as like a frame-by-frame manner. Right, so in this case, for each of the video frame, you can output action label, right? Then for each of the image frames, then you can output the corresponding number of action labels. Then maybe you can do like a majority voting, right, to get a single label. But for many-to-one is you don't output individual label for every frame, but you maybe do some aggregation on the features just to output a single label, okay? So depending on how you're doing this video classification task, okay. So in our real-world application world, right? So there's actually data, taking into the form as a sequence, right? For example, the speech or the audio, right? So is a sequence, and also the language, right? The sentences were presented in the form of a sequence, and there's also other like stock price or maybe some other time series, right? So like if you are using wearable sensor, right, accelerometer, gyroscope, right? So they are also like a sequence, right? Because they have different samples or measures over the time, okay? And we can also, treating images maybe as a sequence, right? So we can, vectorize or rasterize these images as a giant vector, or, process these individual pixels as a sequence, right? So this recurrent neural network is also able to handle this kind of sequence of data. So we can do image recognition. Here we can do digit recognition, and we can also do like a digit in painting, right? So basically we can generate what is the next pixel in this image, right? Just in paint an image. So let's look at a specific example, right? So when we, see how this recurrent neural networks can be applied, okay? So here, the example we are using here is called a slot filling example. So basically, we have like a ticket booking system, right? So if a user, like a chat box, right? So input, okay, I want to arrive Orlando, right, on November 2nd. Then the booking system has to extract the useful information and figure out, right, what's the destination, the time of arrival or departure, and retrieve the necessary flights for the customer or the users, right, to figure out which flight they prefer, okay? So that's the problem we have to figure out, right? So here, the information or the simple two slot we want to figure out is the destination and the time of arrival, okay? So if we are human to extract the information, we know the destination is Orlando and the time of arrival is November 2nd, right? So if we are using a feed-forward network, right? So this is a fully connected feed-forward network, and what we will do is we will process, this word by word, right? So basically, we'll input a word, and we'll go through this network and make a prediction, right? So this is the destination, or this is like a time of arrival, or maybe it could be a time of departure, right? So this is like a two slot. We want to see the probability, right? So in this case, we can represent each word as a vector, right? So we can using some word embedding to generate the feature vector, then go through the network, and we can generate a specific probability distribution, right? This specific input word belongs to the slot, okay? But so if we look at this, right, so we do this one by one, right? So this arrive, if we feed into this network, they may classify this as not these two slots, right? So the other class. So then Orlando, this could be a destination. We classify that as a one of the slot. On will be other, right? November, and the second would be time, right? So time of arrival, or we can, if this is like the same day, we can also consider like time departure. But you may notice that could be a potential issue, right? So what if I have another sentence which called leave Orlando, right? So on November 2nd, okay? So in this context, the Orlando becomes a place of departure, right? Not the destination. But if we continue, doing this one by one, right? So you classify leave as an other, right? Orlando, which will basically give, if you train in this way, will give you the same, probability, right? So basically that tells you, the way you are using this fully connected V4 network, you are not have any memory, right, involved in this network learning, right? Because they don't know, okay, the context, right? If this arrive or this is leave, right? Because you don't have any memory stored. You basically isolate these individual words as individual input to process through this network, right? So that's why we're using this recurrent neural network, right? So hopefully we want to store some of the memory so that we are able to understand some of the context so we can distinguish these two different cases, right? So in this case, right, so we have this input, we have some hidden layer, we have the output layer, right? So we also have like a memory cell, right, to store the memory which we processed before, okay? So in this case, right, this hidden layer activation will be stored in the memory, and maybe in the next input coming, then we'll also consider the memory, right, as additional input, to process the next input, okay? So in this case, right, so the arrive or leave, they have different activations will be stored in this memory cell. Then when we're using that, when we retrieve this memory to process the next word, they will give us, different probability distribution. So let's work through a concrete example, right? So here we have, an input sequence, right? So maybe look like this, right? Very simple. We have each feature embedding is like two-dimensional, right? So here we also make it simple is we make all these weights equal to 1, right? And we don't have bias term, right? And also we're using a linear activation function just for simple computation, okay? So first one, right, we have 1 as your input. So what do we get here is going to be 2 and a 2, right? So we just sum them together, assuming the weights are 1. So we get the 2 as the hidden layer activation. Then we have an output of 4, right? Okay. So we generate output sequence for 4. But here we have to store this. We have to update this memory, right? So initially we initialize with zeros, but now we actually have, when we run the first vector of the sequence, right, we have new activation of 2, right? So we store that in the memory cell. And when we process the second input, right, again, this is 1, then we have to consider the memory here, right? So here we have 2, but we also have this memory 2 come in as additional input, right? So now we have a 6, okay? So this is very simple operations, right? Just to walk through, right, how these memory is able to use as additional input to change the activation, okay? So we can continue working through the last, right? So the second one, and of course, right, we keep updating the memory, right, based on the previous hidden layer activation. Then we can using that the new kind of memory update to process the next input, okay? Okay, when we change, as you can see that, right, because we have this memory cell, right? So if you change the order of the sequence, right? So let's say this 2 moving to the first, it will change the hidden layer activation, right? So that will also affect the value you store in the memory. So they will also change the subsequent input. So based on this intuition, right? So in this case, if you run the RNN, right? So for this particular example, right, arrive Orlando on November, then we will basically process one by one, right? Arrive, we have some activation, then we'll store that in the memory, and we are using that to process the next input, which is Orlando. Okay, we can do this, repeat this again. Okay. So usually, if you want to write a diagram to represent RNN, so you will draw a diagram like this, right? So this is like a self loop, right? Because you generate hidden input, but then you are using that as the additional input, right? For the next processing, right? So you kind of pointing to itself. But if you unroll it, right? So you will basically look like this, right? You have these RNN unit. So the hidden layer activation will be stored in the memory and used as the additional input to the next RNN cell. Okay. And if we run this for these two particular examples, right? So leave or arrive, you can see that, right? So the memory stored in these two examples will be different, right? So although I'm using the same symbol A1 to indicating the memory, but because of the input, right, one is leave and arrive, they will generate different value of the activation. So the memory stored will be different. So the next time, the probability for Orlando here will be, taking account into the context, right? So here maybe we'll predict this is a place of departure, and this will be predicted as the place of arrival. Okay. Okay, so of course, these RNN can also be just like a CN, right? So you can stack multiple layers and you can be very deep. So you can have multiple layers for that, depending on the applications. So that's the basic for the recurrent neural network. And also this long short-term memory, so LSTM, is also a very special recurrent neural network, right? We have their specialized design. So basically, you have input gate, you have an output gate, you also have a forget gate, right? So because this will give you a flexibility, right? What kind of memory you want to memorize, or what kind of memory which may not be very useful. You just want to erase from the memory cell, right? Because maybe that's not related to the task. That's maybe some, unrelated information. You don't want to memorize that, right? Because that's gonna not be very helpful for the network learning. So you have the forget gate to control, right? How much you want to memorize or forget. So basically, the key component, or the special component for the LSTM module. Right, so have 4 input and 1 output. So I'll walk through an example, right? How we can, how this will work. Okay, so this is like a more detailed. So the previous one is just like a very high level, right? So how that look like, but this is actual like a LSTM module, right? So the cell look like. So you will have this input, right? So we have a Z, then we go through activation function, right? So this can be, any nonlinear activation. So here, usually we're using, hyperbolic tangent, right? The 10H activation. And you also have an input gate, right? So this is an input gate control signal, ZI, right? Basically control how much of these you want to open or close, right? So the F is typically a sigmoid function, right? So the sigmoid function scale any of the value between 0 and 1. So 0 mimic the gate is closed, right? You don't allow any information flow through this path. And if the gate is 1, you basically allow all these information flow through, right, for the next processing, okay? So similar for other gates, right? So we have the forget gate. You also have this control signal ZF, and also this sigmoid function to control how much you want to open and close, and also the output. This is also a sigmoid function. You want to control how much you want to output from the cell output gate. So, and we also have this memory cell, right? We call this as a C. Okay, so let's consider that's the initial value you stored in your memory cell. So the process is that you have a z go to this function of g, right? You end up with a gz. Then you also have the input gate, right? fzi, how much you want to use this input data. So you basically do the multiplication. Okay, so this is a sign for multiplication. You multiply them. And also here you have this forget gate, right? So this FZF determines how much you want to turn on this forget gate, okay? And this will be multiplied with the memory cell, right? So let's say the initial value stored here is C, is you want to, how much you want to use for the previous memory, right? C multiplied with FZF, right? This FZF could be any value between 0 and 1, right? Because we are using the sigmoid function to mimic, the open and the close of gate. So now you get like a refreshed memory value, right? So you take into the new input, right? So which is GZ, FZI, plus the previous one, right? The memory stored in the memory cell, multiply with the how much you want to use this previous memory, and you get a C prime, right? Because this is like updated in this current time step. You have a C prime, and you will update that into C prime, okay, in this memory cell. And this will continue go through, right? Another activation function can be a 10H as well. So you have a HC prime. And finally, you multiply with the output gate, right? So how much you want to output from this LSTM cell, okay? So now you have a HC prime times FZ 0, ZL. Okay. So that's just a very simple example to walk through how this different gate or control signal worked, right? So different, how you using the previous memory stored in the LSTM cell and how you can update the memory in the cell. And here is like a more detailed view, right? So, this is basically the cell state in the previous time step, right? So the cell's value stored in the previous state. And also you have an activation, right? Basically the input from the previous time stamp. And this is, this is indicating the sigmoid function, right? So these are all control the gate, right? How much you want to open and close. And you also have these two activation function, which usually using the 10H. And finally, you have the output, all right, of the cell state, right? So that's the updated or refreshed the cell state in the current timestamp, and you also have the activation for the next time step, right? So you're basically using that into the next time step, right? Which you repeat the process from here, okay? So that's the LSTM. Of course, you can make it more complex, right? So not just either for recurrent neural network, the vanilla RNN, or the LSTM to make it bidirectional, right? The bidirectional means, right, so you have timestamp from 1 to t, you process from 1, 2, 3 to t, but you can also process that in a reverse order, right? So you say you have a translation or some sentences, right, or the videos, right? So you can process in the chronic order, then you can also process that in the reverse order, right? So this is like a bidirectional, right? So this way, and you can do this way, right? Basically, you can think about I run RNN or LSTM twice, right, with different order to make more information. There are some limitations for RNNs, right? So the computation over positions cannot be parallelized because you always have to wait, the memory to get updated, right? Using that as additional input to the next cell, right? So in that prevent you do this kind of parallelization to parallel process all these different units. And some of the long-range interaction are bottlenecked by a fixed size memory because you are not able to capture all these different, if you have a very long input, you are not able to capture all these long-range interactions. And next we'll talk about some of the specific use cases or applications, right, for RNNs. So the first is the sentiment analysis, right, classification, right? So for example, you want to classify a review, right, or movie review or restaurant review, right? So you want to give either a positive or negative review, right? You want to classify that. And so the input will be multiple words, right? So or even multiple sentences, right? So the food was really good. The chicken crossed the road because it was uncooked, so it's really funny. So you want to classify, right? If this is a positive or negative. So basically, you will put each of these words into this RN unit, right, to process that. And each of the hidden unit will install in the cell and using that as the additional input when you process the next word. And because, right, so sometimes, we can, decide if we want to ignore some of the word because that may be not related to some of the emotions, right, or the sentiment. So we can ignore some of the words, right, like the food, and only pay attention to a certain word to make the classification. So here, right, so example here is, these may only using these words to make a sentiment analysis, right? So this is like a positive review for a particular product. And we can also using this to apply to vision task, right? So the activity recognition. So we can consider this video as a sequence of frames. We can process each frame using the CN to extract features, right? So we have feature embeddings for each of the frame. Then we can using LSTM, right, to process that sequence of feature embeddings, right, to model that temporal relationship, right? Because the CN you extract for each individual frame don't consider that temporal relationship, right? Because you're treating the frame separately. You are not considering the time-wise dependency. So we want to using the LSTM to model that temporal correlation because a lot of like action recognition depending on strong cues in the temporal domain, right? Like some of the sports, like a long jump, high jump, right? You may have some running, but it's just like the final step may be very different, right? So you want to model that temporal correlation or relationship to make a very distinctive representation for different classes, right? Image description as well, right? So you can maybe generate the CN features, then you can have multiple patches or crops of these images, right? Extract different CN features and using LSTM because we can using LSTM to model that spatial relationship, right? So the scene layout, right? Maybe there's an object in front of another object, right? So there are geometric relationship. So this LSTM can capture that in this case. So this will be really useful for image captioning, right? So similar for the video description as well, okay? Okay, so this is just like a basic or like a detailed architecture may look like, right? So you may design a hybrid CN LSTM framework like this, right? CN to process visual feature from each frame, LSTM to model that temporal correlation, so that you can have a better prediction what class, what action in this particular video. And image description as well, right? So you can have CN extract features and using LSTM to predict word by word, right? So because you want to generate or output a sequence of the description of the image, right? And of course, you can make this LSTM multiple layers, right? So process features at different granularity, so you can stack these LSTMs. Okay, similar for the video description, you can, for this each frame, you process that, right? You generate some average features from the video. So basically this has some representations from the entire sequence, then you can using LSTM to generate description, okay? Okay, all right, so I think that's pretty much I know right now we are all in the transformer stage, right? So this CN LSTM may not be used a lot right now, but for some of the cases, right? So if you don't necessary to using the vision or the transformer, then maybe CN LSTM combined or RN CN combined can still be a very useful or powerful architecture to use. So yeah, so that's for today. So the next class we'll talk about attention and the transformer, and that will be the last class for the deep learning. So I think the 3 class we've kind of quickly gone through all these architectures, right, from CN, RN to transformer. Then we'll dive deeper into very specific or advanced topics, for vision and specific applied to medical image computing. Okay. All right. So thank you for coming. So we'll see you on Thursday.